let us now move ahead with another topic and another point of discussion, namely the generalization of Euler-Lagrange equation. Okay. So, I call this as case C. So, what I am going to discuss in this third case is extensions of Euler-Lagrange equations, or in short I would like to generalize my Euler-Lagrange equations for functions for functionals containing integrands having higher derivatives, right, and several other generalizations which we will see one by one, right. So, under this, let us look at the first type of generalization. Let me call this as case 1. So, in this case we look at functionals containing higher order derivatives. So, functionals containing higher order derivatives, right. Okay. So, in this case, so points that are to be noted, that we can certainly extend our result of the Euler-Lagrange equation to functions which are the integrands of the functionals and which contains higher order derivatives. Let us say derivatives like y double prime, y triple prime, and so on and so forth, right. So, Euler-Lagrange equations can be extended to functionals with higher order, derivatives, right. And further if we consider, further the another issue that we have to consider is the moment we are considering higher order derivatives, our function space will be restricted. So, instead of searching for our extremal in C2 of x0 x1, we have to look at C3 or C4 and so on and so forth, right. So, our function from which the extremal comes out, the function space must be restricted to account for higher order derivatives, right. Okay. So, let us now consider the functional. Let us now consider the functional of the form j y, the simplest possible example in this category. So, j y is from x0 to x1 of f of x comma y prime comma y double prime. So, we have now a function containing derivatives up to second order, right. Oh, okay. So, the moment we introduce extremals having continuous derivatives up to second order, we have to provide extra set of boundary conditions. That is, now my boundary conditions are as follows. My fixed point boundary conditions are y of x0 is y0, y at x1 is y1, and y prime x0 is y prime naught, and y prime at x1 is y prime 1, right. So, these are my boundary conditions, and which means now earlier we were assuming that the extremal y had continuous partial derivatives up to second order. Now, we are going to assume that the extremals y will have continuous partial derivatives up to third order, or in other words y comes from the space C4. Okay. So, let me show how is it possible. Okay. So, what we have is the following. Assume f has continuous partial derivative, f has continuous partial derivatives up to third order, right, third order with respect to our variables. So, with respect to the variables x, y, y prime, y double prime as well, and this means that y must come from C4 of x naught x 1. Why C4? Because this is equivalent to saying that y double derivative must come from C2 of x naught x 1, right, because we have derivatives of y up to second order, and we need, for our Euler-Lagrange derivation of Euler-Lagrange equation, we need the variable with the highest order, highest derivative to be at least C2, or the variable that we have y must be C4, right. Okay. So, then we have to rewrite. So, rewrite our function space. So, now my S becomes the following set of functions. So, it contains all y in C4 of x naught x 1 such that y of x naught is y naught, y of x 1 is y 1, y prime of x naught is y naught, y prime of x 1 is y 1, right, and our perturbation set H is eta also in C4 of x naught x 1 such that eta of x naught is eta of x 1 is eta prime x naught is also eta prime x 1 is also equal to 0. So, the perturbation set is such that the values as well as the values of the first derivative at the boundary points, they vanish, right. So, with this we are ready to describe our Euler-Lagrange or equation or the necessary condition for the existence of the extremal. Okay. So, suppose, well, to do that, let us now number some of the equations. So, let me call this equation that we began with as 1. Okay. So, suppose 1 has a local extrema, right. It has a local extrema at, let us say, at the function y which is in S, and let us say that the perturbation to this extrema is y hat, which is given by y is equal, y hat is equal to y plus epsilon eta, right. So, this is my perturbation to this function, right. So, from regular Taylor series expansion, I can rewrite my integrand in 1, which is f of at the perturbed value, which is f of x comma y hat prime comma y hat double prime in terms of the value at the extremal point or at the extremal function. So, this is also equal to f at x comma y plus epsilon eta comma y prime plus epsilon eta prime comma y double prime plus epsilon eta double prime, right. We further see that once we use Taylor series, we get to the point where this is also equal to f of x comma y prime comma y double prime plus epsilon eta. The first order terms are as follows: del f del y plus eta prime del f del y prime. Notice that the first these two terms are identical to our derivation of Euler-Lagrange in the standard case, but now we have an additional term which is eta double prime del f del y double prime, right. That comes from the fact that now f is also a function of y double prime, right, and plus I ignore the higher order terms, right. So, plus higher order terms, right. I do not care about the higher order terms for epsilon sufficiently small. Okay. So, which means that my variation in the functional which is j of y hat minus j of y will be the necessary integration, and after plugging in the values of the integrand via the Taylor series, we get that up to first order the right hand side becomes integral from x 0 to x 1 eta del f del y plus eta prime del f del y prime plus eta double prime del f del y double prime, right. So, times dx plus order epsilon square terms, right. Okay. So, then we redo the exercise that we did in the standard Euler-Lagrange case, that is we are going to change this second and the third term using integration by parts, and then we apply the boundary condition. So, notice that this particular quantity is also equal to negative of integral of d dx of del f del y prime, right. This is coming due to integration by parts and using the boundary condition, that is the perturbations eta, they vanish at the boundary, right. And finally, this one again we have in the third term we have to do integration by parts twice, and again use boundary condition, all the 4 boundary conditions, to arrive at the point that this integral is eta times d dx 2 of del 2 f del y double prime of dx, right, of x naught to x 1, and finally, we substitute all these terms in this integral expression to see that this is also equal to epsilon times x naught to x 1 times the integral of eta times del f del y minus d dx of del f del y prime plus d dx square of del f del y double prime, right, times dx. Okay. So, we see that the extremal, again we use a similar variation of lemma 2 that we showed in our lecture 2 to come to the fact that, well, we must have that the extremal is 0 provided this variation is 0, or which means that this variation must be 0 for epsilon sufficiently small, and from here we come to the fact that using, I must say that using the generalized lemma 2 discussed in our lecture number 2, we arrive at the fact that this quantity inside the bracket will be 0, right. We arrive at the fact, let me denote this bracketed quantity as E of x, which is also identically equal to del f del y minus d dx del f del y prime plus the second derivative with respect to x of del f del y double prime, this is set equal to 0. So, this is the extension of the Euler-Lagrange equation for functions containing derivatives up to second order. We call this extended Euler-Lagrange as Euler-Poisson equation. I denote it in shorthand notation as EP equation. So, the extended Euler-Lagrange equations for functions containing higher order derivatives are also known as Euler-Poisson equations. Okay. So, let us look at an example in this situation. Okay. So, let us look at this particular example. So, I am given and I am asked to find the extremal. I am asked to find the extremal for j, which is given by the integral from 0 to 1, which is y double prime square minus 2 rho y of dx, where rho is a constant, and y of 0 is equal to y prime 0 is equal to y of 1, right. So these are my boundary conditions, is equal to y prime 1 is equal to 1. So these are my 4 sets of boundary conditions. So we have to find the extremal for this functional. Notice that this functional contains derivatives up to second order, and my Euler-Lagrange equation, or my generalized Euler-Lagrange or Euler-Poisson equation, the EP equation, it reduces to, after plugging in this expression for f, right, in Euler-Poisson, we see that my equation reduces to the following fourth order ODE, or ordinary differential equation, which has the solution of the form, y of x is equal to rho by 4 factorial x to the power 4 plus c1 x cube plus c2 x square plus c3 x plus c4, right. Okay. So Ci's are constants. Okay. So Ci's are constants. So using all these, we have 4 constants and we have 4 boundary conditions here. So we can very conveniently eliminate all these unknowns of the problem. So if we use the fact that the first of the 2 boundary conditions, y of 0 is y prime 0 is equal to 0, we see that this is also equal to C3, gives us C3 is equal to C4 is equal to 0. Further, if we use the fact that y1 is equal to y1 prime is equal to 0, the set of the other 2 sets of boundary condition, we get that C1 comes out to be negative 1 plus rho by 12, and C2 comes out to be 2 plus rho by 24, right. It is all about a matter of algebra to solve all these constants, and finally my expression for the extremal is the following polynomial. So this is a 4th order polynomial containing x to the power 4 plus this constant times x cube plus this second constant times x square, and we do not have any factors of x and the constant factor. So this is my extremal to this 4th order functional. Okay. So that completes the solution to this example. Okay. So let us look at some specific cases in this generalized scenario. So there are 2 specific cases I want to highlight. Let me call this as A and B. The first case is if my functional j of y does not contain y explicitly, then my Euler-Poisson reduces to the following equation. I get that this is also equal to d dx of del f del y double prime minus del f del y prime is equal to a constant, right. It comes via the direct removing certain unnecessary terms where we have involved derivatives of y and then integrating once to come to this point, right. So instead of solving a 4th order ODE, we are solving a 2nd order ODE, right, or a 3rd order ODE in this case. Okay. The second special case is if my functional j of y does not contain x explicitly, then my Euler-Poisson reduces to the generalized Beltrami identity. So, in this case my Beltrami, so I have, this is the case where we have the generalized Beltrami identity to be satisfied, which is basically this following function h of y, y prime, y double prime, which is also equal to y double prime del f del y double prime minus y prime times d dx of del f del y double prime minus del f del y prime minus f, right. Okay, so this is all set equal to a constant. So, that is my generalized Beltrami identity that we instead solve in this special case. Again, this is a reduced order Euler-Poisson equation. Okay. So, let us look at an example, another example in this discussion. Let us extremize this functional. So, I have j of y is equal to integral from x0 to x1 integral of 1 plus y prime square whole square divided by y double prime dx, right. So, we see that we do not have an explicit dependence on y in this particular integrand. So, this particular integrand falls under the case scenario A, right. So, what we can do is, so what we see is no explicit dependence on y, right. So, what we see is that now that my Euler Lagrange or my Euler Poisson equation reduces to this underlined expression, which is d dx of del f del y double prime minus del f del y prime is equal to a constant, right. So, once we plug in all the values of the expression, we should be able to solve. However, there is a further simplification that we can perform. Notice that this integrand is also independent of any x. So, there is no explicit x dependence on this integrand, which means that we can also use the Beltrami identity, right. So, what we said is the following, right. So, since no explicit x dependence, we can use the Beltrami identity h of y prime comma y double prime is given by y double prime del f del y double prime minus y double prime d dx of del f del y prime y double prime minus del f del y prime minus f is equal to the constant C2, right. So, this is my Beltrami identity, and further in the previous slide we have seen that this particular quantity is a constant. Let me call this as C1, right. So, this particular quantity in the bracket is nothing but equal to C1 from the previous slide, right. So, what I have is the following equation to be satisfied: y double prime del f del y double prime minus y prime C1 minus f is equal to C2. Okay. So, this equation is relatively easy to solve. All I have to do is to plug the value of f. So, when we do that, we see that we get the following expression. So, we have simplified the expression now: 2 minus 2 times 1 plus y prime square whole square divided by y double prime minus y prime C1 minus y prime C1 is equal to C2. So, that is the simplified expression. Okay. So, then let us now say that this is K1 which is minus C1 by C2, and let us say my K2 is, so I am introducing two sets of new constants. So, my kappa 1 is negative C1 by C2. Well, the more convenient constant will be minus C1 by 2, and the second constant we can introduce kappa 2 to be C2 by 2, right. So, when we do that, we have to further, well, this particular equation, let me call this as star. This is as such not very easy to solve. The way we are going to solve is, we are again going to solve it parametrically, right, or we are going to find y as a function of a parameter and x as a function of the same common parameter, and that will be our final solution, right. So, we solve, we are going to solve. So, let me just first rewrite this expression in terms of these new constants. So, I see that my new equation is y double prime times kappa 1 of y prime plus kappa 2 divided by 1 plus y prime square whole square is equal to 1. Let me call this as double star, right. So, we solve double star parametrically. We solve double star parametrically from now on by assuming that y prime is equal to tan psi, right. So, this is the starting assumption for our parametric solution, right. So, which means that my quantity 1 plus y prime square is secant square theta, right. Okay. And further we also have second derivative of y with respect to x. So, we need to find out with respect to psi, right. So, my second derivative of y with respect to x is secant square psi times psi prime, because my y prime was tan psi. So, all I had to do was to differentiate this underlined expression just once, right. So, we got y double prime. So, we are now in a position to substitute all the quantities in the Cartesian frame in terms of this parameter psi. So, we see that my double star expression can be reduced to the following form: kappa 1 cos psi sin psi plus kappa 2 cos square psi times psi prime is equal to 1, right. So, after substituting all these expressions for y double prime, 1 plus y prime square and y prime in my expression double star, I am going to get the following expression completely in terms of psi, which I can integrate. Let me call this as triple star. I can integrate triple star to come to a point where I can find the solution. Notice that this prime is derivative of psi with respect to x. So, I can integrate and find the x coordinate by integrating triple star. So, we see that x comes out to be the following expression: kappa 3 plus 2 kappa 2 psi plus kappa 2 sine of 2 psi minus kappa 1 cos of 2 psi. Let me call this as 4 star, right. So, I integrate and we see that this is my 4 star. Okay. So, I have found my expression for x. To find the expression of y, note that I had y prime was equal to tan psi, right. So, this gives me that dy is equal to tan psi dx. So, dy is equal to tan psi dx, or just substituting, differentiating x with respect to psi, we can easily get this quantity dx. We see that dy, so well, I need to keep renaming these expressions. So, essentially we are going to use this 4 star. So, using 4 star to substitute this dx, and then we integrate with respect to psi, I can get the final expression for y. Y comes out to be kappa 4 plus 2 kappa 1 psi minus 2 kappa 2. So, I am just giving the solution to this problem. Students are expected to go through all the steps and do the integration. This is not a very difficult integration to perform. Plus kappa 1 sine 2 psi, right, and let me just denote it as 5 star. Okay. So, which means that the solution is given by 5 star and 4 star here. Okay. So, my 4 star and 5 star are my parametric solution given by x of psi comma y of psi, right. Okay. So, we are going to end the discussion in this lecture by mentioning one important result, namely that the Euler-Poisson equation can be further generalized for functionals containing integrands of higher and higher derivative. So, what I meant to say is the following. Let us look at this most general case, right. The most general case is j of y is integral x naught to x1 f of x comma y prime, y double prime, and so on. Let us say up to y nth derivative. The function integrand contains y, the derivatives up to the order n of dx, right. So, the extremal, my extremal y satisfies the Euler-Poisson equation, which is of this following form. Notice that this conveniently reduces to the Euler-Lagrange as well as the Euler-Poisson equation for functionals containing derivatives up to second order. So, this is the general version of Euler-Poisson. So, this is my general Euler-Poisson. Okay. So, let me rewrite this expression. So, this is this minus 1 to the power n minus 1, the n minus 1th derivative of x with respect to x of del f del y n minus 1, and so on so forth, right. The last quantity that we will have is the derivative of partial of f with respect to y, and this is set equal to 0, right. So, this is my generalized Euler-Poisson for functions containing derivatives of any order, right. So, let us now end this lecture session, and let us end this session by mentioning that we have several other ways to generalize the Euler-Poisson. Namely, how about looking at the case where we have multiple dependent variables or we have multiple independent variables. We will see that those sort of equations frequently arise in continuum mechanics, especially in planetary motion as well as standard Newtonian mechanics. So, thank you for listening for this lecture. Thank you very much.